In today's videos, we will take a look at linear inequalities in two variables. The first thing we want to make sure we distinguish is the difference between a number line and then the Cartesian plane. We use a number line when we are going to just graph or represent one variable. So if we have something like x is greater than 3, that's just referring to the relationship between one variable. So that goes on the number line. The Cartesian plane will be used again when we're talking about two variables. So in today's homework and lesson, we'll be using the Cartesian plane, which refers to the x and y axis. What you're going to be doing for these is we're just going to graph the inequalities. To do this, we'll use just a regular Cartesian plane, and basically you just want to graph the equation as if it was just an equal sign. So I can take x plus y equals 4, and I can graph it, and I can do this in any number of various ways. I want to do this one by doing the intercept. So if I put in 0 for x and solve for y, my y-intercept will be 4. And if I go to solve for the x-intercept and plug in 0 for y, my x-intercept is 0, 4. So I go and I plot these on my graph, and then you go and you note what the inequality is. Since this is less than or equal to, the equals to part indicates a solid line. So if that line was not there, you would create a dashed line. So we'll just connect those right here. The inequality basically then refers to the area in which makes the statement true. And you'll notice in the graph that the line kind of divides itself into two sections. There's a section below the graph and there's a section above the graph. And basically what you need to find out is which one of those sections will be true. So what you can do is you can do this by testing a point. Easiest point to test is 0, 0. So we'll test here. And if I put in 0 for x, 0 for y, and I see what it does to the inequality, you'll notice that 0 is indeed less than 4. So this is a true statement. And since the point is true, we will shade the true side, which happens to have the point along with it. Now, if I were to randomly have selected a different point, let's say I would have selected 4, 4, and I would have plugged it in. It should hopefully be false since it's a non-shaded side, and if we plug that in, 8 is less than or equal to 4. That's a false statement. So that would refer to that all that side would be false. And again, what the shaded side represents is that any point within the shaded section would indeed make the inequality true, whereas any point in the false section would make it false. Since the line is solid, that would also include points on the line to make it true. Another way to graph inequalities, or to shade inequalities, is to put it into slope-intercept form. So we can bring over the 3x, divide by 4, and graph it using slope-intercept form. So I'll plot 3, I'll go down 3, right 4. I can go up 3, right 4. And again, because this is a less than sign, that means it could be a dashed line. I'll make a dashed line right here. And let's say that we test 0, 0. And I can plug it either into the original or into the new one. That won't make a difference. So let's say we test it into the original. 3 times 0 plus 4 times 0 is less than 12. So is 0 less than 12? That's true. So we shade below. Now, what I want to point out is that once we get it into slope-intercept form, meaning that y is listed first, as you can see here, and then it's mx plus b, the sign can tell you what way to shade. So since that is less than, we shade below the line. If it was a greater than symbol, we would shade above it. Let's take a look at a couple more. Let's go ahead and graph this one. So I'm going to do this by let's make the slope intercept. Negative y is less than or equal to negative x plus 4. Y is greater than or equal to x minus 4, again, because I'm dividing by negative 1, so that flips the sign. I'll graph that by putting negative 4 and going up 1 over 1. Since it's an equal to, it's going to be a solid line. And because it's greater than, we're going to shade above. Now, you may have noticed that there are two equations in this example. So we're also going to graph this line on top of the other one in the same Cartesian plane. X is greater than or equal to negative 2. Having just x, that means it's going to be a vertical line. So we're going to go to a vertical line at negative 2, and it's going to be solid. And since it's greater than, we're going to shade to the right. And the key thing about this example is that the word and is in here. So that means the intersection or the overlapping. So we're looking for the overlap of these two. And you'll see it kind of right here, right in the middle. And if you look how it's divided into 4 pieces by the 2 lines, there's nothing down here, so that's not a solution area. But in this left area, there's only that brownish red ink. So that's actually not part of the solution. This down here is actually not part of the solution, but where the 2 overlap is. So we're going to make that a little bit more defined, that the solution area is where the 2 colors overlap. So any point within those would satisfy both equations. Now, let's change that around though. Let's say instead of and statement, it was an or statement. If it's an or statement, it means it's the union of the 2. Therefore, I would kind of have to retract what I just did because it would be the joining of the 2. So not only would it be this section that we just filled in, but because it's the union, it would also include that section and now this section. And the only part that is not included now is this area down in the left corner. In the last section of the chapter, section 3.5, Intro to Functions, and we just have some definitions that you may be familiar with. The first is independent versus dependent variable. In an equation relating x and y, if the value of the variable y depends on the variable x, then y will be the dependent. Whereas if the value of the variable y depends on the variable x, x is considered the independent variable. Next definition is a relation, which is just a set of ordered pairs. A function, which is the relation in which for each value of the first component of the ordered pairs, there is exactly one value of the second. Domain is just your x values of a point or a function, and the range is your y values. So looking at the first example, there's a couple of questions. First of all, is the relation of function? State the domain and range then of each. For part A, the set is 0, 3, negative 1, 2, and negative 1, 3. The first part is it a function? The answer would be no, it's not a function, because a definition of a function states that basically each x value is going to one distinct y value. Other words, there's not going to be any repeats of the x values going to different numbers. So you'll see that we have repeats of negative 1 and they go to different values. So that tells you right there that it's not a function. The domain of this are your x values. So my domain is 0 and negative 1, while my range is 2 and 3. Part B says 5, 4, 6, 4, 7, 4. I know it's a little cut off, but those are the numbers. Again, 5, 4, 6, 4, 7, 4. And to answer the first question, is the relation a function? Well, we kind of look at the domain. We have 5, 6, and 7. That is the domain. So there's no repeats in the domains going to different values. So this is a function. Again, the domain being 5, 6, 7, and the range being just 4. Still asking the same questions, let's take a look at number 2. Number 2, we have a linear line with a positive slope, and I want to know if it's a function. Well, if you look at it, each value of x goes exactly to one point y. So, yes, this is a function. Now, if we talk about what the domain will be, the domain is your x values, and if you notice your x values, they're slowly continually going right, and they're slowly continuously going left without a break. So our domain will actually be all real numbers since they continue on in both the right and left direction. The same actually can be said for the range. Range meaning your y values, and this is slowly going up, and that is slowly going down. So the range is also all real numbers. You can also see if this will be a function by the vertical line test. Vertical line test is obviously meaning a vertical line, and you basically scan it through the graph, and as long as the vertical line only touches the graph at most one point, that will tell you it will be a function. Now let's take a look at number 3. If I'm thinking about vertical line test and I'm scanning the graph left to right, notice that the vertical line will only hit once at every time. So it does indeed meet the requirements and is a function. If I look at the domain, my x values, it continuously slowly goes to the left and again goes to the right, and it covers all of my x values. So the domain here is also all real numbers, while my range is a little bit different because you see that it peaks right here, but it continues to go down forever. So my domain goes to negative infinity, or from negative infinity to positive 3, because there's nothing above here, it stops at 3. We're going to continue this in the next video. It should just be 1 or 2 more minutes from there.